can be seen from the reaction. But sometimes it does not like that. So we have first equation, chemical reaction, and we have the second chemical reaction. Have a look at the first one. The first reaction is just much simpler than the second one. So this red law suggests that two reactions occur via different mechanisms. You know itself actually I and Br, so iodine and bromine, actually only one group in the element table, you know. So, but you know, they have different, very significantly different in the reaction with hydrogen. The first, it is very simple. It is only an elementary reaction, one step, whereas the second one is certainly involving multi-step process. That's why the equation of the rate, the second reaction, is more complicated. Later on, in the second part, we will soon explore how to obtain complicated rate laws from the mechanism. Let's go for finding rate laws by experiment. Two common methods for determining rate laws. First is method of isolation. We set up reaction, so one reaction is in excess. Any change in rate will be due to change in other reactant. We repeat it for other reactants as like that. So we have that equation. I think you already learned this in the secondary schools. So it is not quite hard for you to find it, to find the rate laws by isolation method. And then we go a bit further because this experimental setup actually already be done in the secondary school. Now we have integration of rate laws. We already discussed for order reaction. Here, let's say for a reaction A as a reactant becoming a product, then a rate law can be shown as the equation in the equation. So then we get it as I written earlier in the blackboard. So the R, or the reaction rate, is equal dA per dt. And that one is equal to minus rate constant time the concentration of reactant A powered by N. To make it clearly, let's go back to the board, the new board. Here, so if we have this, A is reactant, okay, and becoming a product. So we know, as we already learned 5 minutes ago, let's say this one A, then the rate constant is equal to this. Okay. And that one in integrated rate law is equal to Ka and powered by the order of the reaction. This is order of reaction. Can be 0, can be 1, can be 2, can be 3, n. So for order reaction, simple one, for example, like that one, like the A becoming a product, it's just easy. Let's say that one is first order reaction, can be just written by a 1. This n is 1. So Ka 1. The question is, if we have second order, for example, A react with B becoming a product here, then the reaction can be dA dt equal to Ka for second order reaction is 1. Okay, so the question is, we have this is called by second order reaction, but if A concentration, initial concentration A is equal that by B, initial B concentration, that R will be represented by Ka 2, sorry, 2. This one is 2, second order. Okay. How we get the, by learning this later on. So what we learn is, first we learn on first determining Kg, second we determine half life, and third we determine K, K by gravity. So equation. This one is equation. That's what we learn. From over there, let's go to first order reaction. Go to first order reaction. First order. We have this one, reactant, yes, and that one product. We can write that R is equal to dA per dt, and that one is equal to Ka. So we just integrate this to get the equation. So dA per dt again minus Ka, and we can rearrange this equation to become dA per dt, dA per A, sorry, equal to, okay, integrate from 0 to t, from A0 initial A to A. So what we get from that, this is mathematical solution. From this equation we get this ln A from A0 to A is equal to minus kt for 0 to t. So meaning that can be written like ln I I0 equal minus k. So this is our first objective to get it. So we determine the equation of kt equal to Then, by plotting, go back to the presentation. So that's what we get. By plotting ln of concentration of A versus T, can get a straight line of slope minus k. So the first order, so we can get slope like that. So this is so the right one. By plotting ln A to T, then we get the straight line. Or I can show you in the presentation in my whiteboard. So rearrange of this from that one. Ln A is equal to ln I0, okay, minus kt. When we plot this one is ln A, okay, by versus t. Let's say this y equal to this is b minus ix. So this one is x and that one is y. So what we get is equation like this, in the graph like this. That one, the slope is equal minus a, and that one is a minus k. The constant, the rate constant. And here is the value of b, and that one is ln A0. Like that. So what happened from the equation of this can be also written by A equal to A0, this concentration of course, time minus kt. Okay, and we can also make create the graph from that. Okay, this one is A per A0, and that one here is T. So we can get the graph like this. You can see again on the presentation, on the left side of the graph, when the value of k is smaller, like given by the line in blue color, see, then the formation of the products is bit lower or the decrease of the reactant